Basically, I'm doing a PhD in geophysics, and I study how the continents move and change shape over time. So my talk today is going to focus on Tibet, but before we get to that, we have to know what we mean by the continents. So these are the layers of the Earth. We have the solid inner core, and then the liquid outer core, then the mantle, and then the crust. And those are the compositional layers. Importantly, for the purposes of this talk, the mantle is solid, although lots of people think about it as the plates kind of floating around on a sea of lava. That's not what's going on. There's also a different kind of way we could break this up, and that's in terms of the mechanical properties of the different layers. And for the purposes of this talk, the important ones are the lithosphere, which is the very outside part where heat is transferred by conduction. So you can think of that as kind of an elastic lid in some sense. And then, Ophelia's going to hate this. And then underneath is the asthenosphere, which is kind of weak and moves around relatively rapidly. And in the oceans, we have crust that's kind of 7 kilometers thick and quite dense. And in the continents, it's less dense and thicker. So throughout this talk, I'm going to be talking about rocks flowing. But when I say that they're flowing, I mean that they are fluid, but they're not liquid. So the picture here shows a typical rock from the mantle. It's green, actually, even though it's normally drawn as red. And it's still solid at the kind of temperatures and pressures that we see in the mantle, but it's at maybe 80% of its melting temperature. And what that means is that it can move by these processes called creep. And so we can still get this kind of convection. This is just an example of a simulation. No one quite knows how it works. We can still get this convection, which is rapid on kind of geological timescales, but without the rock actually being liquid. Okay. So I said I study the continents, and there's a question about why that's interesting. So we have these tectonic plates that are the chunks of lithosphere moving over the Earth's surface. And the idea of plate tectonics is that these are relatively rigid blocks, and then along their boundaries, they just move past each other. This is a map of all the earthquakes from the 1960s to 2013 or something like that. And what you can see is that this idea of plate tectonics works really well in the oceans. We have these kind of narrow bands of earthquakes just along thin lines, and that's where you've got these rigid plates just moving past each other. But in the continent, something different's going on. We have earthquakes over a really huge area, and so that's what makes them an interesting place to study. If we look here, and this is the earthquakes again, the idea is that basically we can't use plate tectonics to describe this. If you look at Greece over here, there's no way you could say what plate that was on. It's just full of earthquakes. There's distributed deformation everywhere. And so we need a different system for describing what's happening here. And that's what makes it interesting from a geophysics perspective. It's also important from a societal perspective. So now I've only shown the kind of larger earthquakes, and the green earthquakes here are ones which have already killed over 50,000 people in the historical record. Most of them are from early last century. In the background here, I've shown the population density, and it's on a logarithmic scale. So black is less than 1 person per square kilometre, and white, here in the Gangetic Plain, is over 1,000 people per square kilometre. So what you can see is that we have earthquakes, and we have large numbers of people. And the blue squares are megacities, so places which currently have over 10 million inhabitants in their urban area. So once we have this idea of distributed deformation, so we could have earthquakes anywhere, and we also have high population, this is clearly a big problem. And one of the kind of questions in this field is, when will we have an earthquake that kills over 1 million people? We would rather that didn't happen, obviously, so understanding what's going on is important. But I said I would talk about Tibet. So what's happening here? Well, this is the kind of motion of India over time. It's moved northwards, and about 50 million years ago, it started colliding with Eurasia. The reason it doesn't look like that on that map is because Eurasia has been squashed by the subsequent collision, and so it's showing you how much shortening there's been. And so these plates are being pulled together, and they squash and form Tibet. And there's been a long-standing question about how we should think about this. So I said we can't think about it in terms of plates, But should we think about it in terms of faults all moving past each other? Obviously, these are how the rock actually moves in earthquakes along faults. But is it a useful way of looking at it to understand what's going on? Well, the problem with it is that we don't really know where all of the faults are. Some of these big strike slip faults, perfectly easy. Lots of earthquakes. I mean, a shallow earthquake is 10 kilometers depth, and they often don't break the surface. So we may well not know where all the faults are. So an alternative suggestion is to kind of view it with fuzzy glasses. So this is the long wavelength topography of Tibet. So just ignoring everything that happens at small scales. And then when we're thinking at length scales that are much longer than these faults, we can start to think about it as a fluid. So if we're going to think about it as a fluid, what are the forces that control how it moves? Well, there's essentially two things that are important. The first is plate driving forces. So that's what's pushing India to collide with Eurasia. And actually, this is indirectly to do with indirectly gravity as well, right? Heavy plates get pulled down into the mantle, and that subduction drives the rest of the plates to move. And similarly, at mid-ocean ridges, we get hot stuff coming up and pushing plates apart. And then the second force is gravity. And the question is, which of these are important? So you can imagine you could have a situation where the plate driving forces are much stronger than gravity. You basically squash everything really hard and the gravity is not important, and your mountains grow as high as they like, unlimited. You can also imagine that gravity could be much stronger than the plate driving forces, in which case everything just stays flat. You just uniformly thicken things. You can't have mountain ranges. Luckily, for my purposes, on Earth, they're about the same, which makes things more interesting. So what we have then is that you can compress things up to a certain height, and then they start to collapse again under gravity. They can't get any taller. And so we have mountains that are a few kilometers high, and they start to develop these flat tops at the level where the gravitational forces are balanced by the compressional ones. So how does this relate to Tibet? If we want to come up with a fluid model, we first need to think about what do we actually want to explain about how Tibet works. So what I've shown here is an elevation profile going from south to north through Tibet. The spiky bit on the front is the Himalayas, which are a lot higher than the rest of the plateau. But what you can see is that actually, once you've gone over that steep front, the top is very flat. So it has a steep front and flat top. Second thing is that it's all spreading out perpendicular to the front of the mountains. So the purple arrows here are how the mountain fronts moved in earthquakes, and the black arrows are like a much better version of the GPS on your phone, measuring how fast all of the stuff is moving. And it spreads outwards radially. And the third thing, which Flo and Matt might understand, but you don't need to worry too much about, is that the south and the north of Tibet work differently. So in the south we have extension that goes east-west, as I'm sure you remember. That's what these beach walls show. And then in the north we have much more strike-slip motion. Sorry, Ophelia, you know that too. Okay, but if when we're doing this modelling, the kind of key thing is what happens at the edges of the flow. So if you're going to plonk a pile of fluid somewhere, what's the boundary? What's underneath? And I told you before that we've got this kind of rapid convection going on in the asthenosphere underneath the lithosphere. So one possible model is just that that's kind of decoupled and the plates can just float around freely on top, in which case the material on top can just float around freely, in which case there's no reason for there to be any kind of imposed velocity on the bottom. So you just get the same horizontal velocity all the way through your fluid. And in that case, you get very gentle topographic slopes. And a fun fluid analogue of this is to put tahini into golden syrup, which Matt describes as completely disgusting, but that's fine. So what you can see, we've even got isostatic compensation actually, but we won't go into that. So you can see that you've got like these very shallow slopes here. It's all just kind of a smooth, gentle profile. Okay. The other end member is that the base of the fluid is stuck. Right, that it can't slip on the boundary, so you impose that it has no velocity on the bottom, and so the velocity gets faster throughout the fluid. And this gives us a very different shape, where we have these kind of steep fronts and flat tops. So that's more similar to treacle on a plate. This is meant to be one blob of treacle, but it's quite difficult to blob treacle in one go. But what you can see here is that as it spreads out, we have a sharp nose on the flow, and then a flat top. across it, and that's because the bottom boundary is stuck. So how should we think about Tibet? Well, initially, everyone thought about it in terms of zero shear stress, and that's because of this mantle convection idea that I was talking about earlier. You think everything's moving freely, why would there be anything else underneath? It's also because the calculations are easier if your horizontal velocity doesn't change with depth in the flow. The problem with that is it doesn't explain how we get this extension in the southern part of Tibet. And so there were kind of various suggestions about how this could work. And this one at the bottom here just shows how as you squash Tibet, it gets taller, but also deeper. The root of it gets deeper. And eventually the idea is that this convection will just pull that root off. And then that makes it kind of rebound and collapse under gravity. Which is pretty complicated, right? Doesn't seem like the kind of Occam's razor solution to the problem. And also, it's not true. So if we look at a map of lithospheric thickness, so yeah, how thick that kind of cold lid is, then you can see that under Tibet, so over here, it's actually pretty thick. It's not clear that anything's fallen off. But if it's not hot underneath, then we need another kind of model for what's going on. But if we look at the earthquakes going from south to north beneath Tibet, all these circles are earthquakes, then what we see is that they keep going underneath Tibet. Now, earthquakes can't really happen, well, it's a subject of great debate when they do happen and when they don't, but they don't happen in really hot places. So probably we don't have very fluid kind of hot material going on under here. And what we think instead is that India, when it collided with Tibet, has gone slightly underneath. And so it provides a kind of rigid base. And so what's actually happening is that the southern part of Tibet is like the treacle on a plate. And the middle part of Tibet, or the northern part of Tibet, is more like the tahini on syrup example. Which makes it a bit more complicated, but there you go. I should also say super viscous treacle and tahini. I mean, yeah, you're not going to see this stuff moving. Okay, so that explains some of how Tibet works. But there's some other observations that we can make about mountain ranges in general, and it would be nice if we could explain those too. The first is that a lot of mountain ranges are curved. So Tibet, if you draw actually an arc of a circle, you can make one that follows the curve there. The Zagros Mountains, though, in Iran, which is kind of a similar situation, they're pretty straight. There's a few places marked on there where they're not, but that's maybe a bit different. And then you have the Suleiman Range, which is in Pakistan, and this is this like nose shape that sticks out into the plain. And so we'd like to be able to explain why these things happen. So the idea that we use here is essentially that if you start with a straight mountain range, because you can imagine if you're just squashing things in a straight way, then they go straight, and then you let them spread out under gravity, then they start to become curved. So here's the golden syrup again, and we start with a straight line, and then you can see it gradually gets more and more curved over time. It's quite nice because that one actually works. And if you simulate this, then you find that, yeah, you get this kind of increase in curvature through time. And that explains why Tibet is curved, but the Zagros Mountains aren't really. Because the Zagros Mountains are much younger, and if you've got kind of the same other properties, then that's the same. Unfortunately, the Suleiman Range, which we saw before is the most curved, is also the youngest one of these mountain ranges. So what's going on there? Well, then we come back to this idea of what should we do about the base. And what we think is happening in the Suleiman Range is that you get a packet of sediment underneath where this thing is spreading out. And so then that suddenly provides this kind of stress-free tahini on syrup boundary condition. And that means that just one part of the mountain range can spread out much faster than the other bits. And so we get this kind of nose shape, which is kind of weird, but it shows that you have to think about a lot of different things. What you might have noticed in this talk is I haven't talked about anything that I've done. So what is my job in this? Well, what I'd like to think about is what happens when you change what's going on. So in Tibet, I told you that under the main part here you have this Indian shield, but then when you come over to the east, you can see here in the Google Earth picture, it looks like it's kind of flowing around the corner, right? And so you change what happens at the base. And if we know how high it was at different times in the past, then we can start to think about when does this need to have changed, and can we say something more about the physical properties of the lithosphere by looking at it. The problem is that essentially my code's not working yet, so I can't tell you what happens, but there we go. Cool. So to conclude, essentially Tibet is a bit like Treacle.